All right, hello ladies. This is section point 10.6 notes. We have a lot to cover, as you can see from the outline and the examples that I want to go over. I just want to make sure, since I'm not going to be in class teaching this, that I give you plenty of examples to look at. I'm also going to be writing a lot of things down in advance, so if you want to, such as you see on this slide now, so if you want to pause and then write it down and then play to continue, you're going to need, I don't know, I'm going to try at most to just do 3 videos. And not to go over that. I don't like going over 15 minutes because YouTube gets funny if I go over 15 minutes in terms of uploading my videos. So if I get close to 15 minutes, I will probably stop and start a new video. So you're going to need some time. I would say give yourself a good 2 hours to go over these notes thoroughly and make sure you understand. We will be moving on. So when I come back on Tuesday, I might quickly answer some last minute questions about this, but we're going to have to move on to 10.7, which is Taylor's series. So make sure you really understand these notes, and hopefully you're not waiting until Sunday late at night to watch it. The quiz this week will be in Gradarius, and I'll upload that information a little later, or depending on when you're viewing it, it's uploaded already. There are going to be some questions that I'll ask scattered throughout the videos, so make sure you watch the videos first before you start the quiz. And also there will be questions from 10.5, which is ratio root test, and also I still plan on breaking in at least one question from the last exam you guys just took. All right, let's get started though. So, and hopefully my voice is okay. I am a little under the weather, so hopefully I don't sound too monotone and you all can hear me okay. All right, let's get started. So to introduce, so before we start the examples, I want to sort of introduce what is meant, or what we think about, or what we want to start thinking about when we look at a power series. So let's just look below. So we have 2 infinite series below, and so notice one is called f of x and one is g of x. And in f of x, so in A, we have a sub n, times x minus c to the n as our term. And then I sort of wanted you all to look to see what happens if I string out a few terms. And so we see the first term is going to be a sub naught times x minus c to the 0. So we know that there is going to go to 1. And then we got a sub 1 times x minus 1, and then a sub 2 times x minus 2 squared, and so on. And then in g of x, it's a times x to the n. So hopefully you're noticing, and just think about it for a minute. Pause the video as much as you need. Think about what you notice between the two. You should notice that in one, a sub naught changes, whereas in the other it stays fixed, right? So that's sort of the first thing you should notice, is that one, the a sub n changes, the other it stays fixed. Also, you should notice that there's a c added here that's not in the second function, okay? But if a was fixed here and c was 0, these two would be the same, correct? Right. And so you should also notice that in B, what type of series does this look like? It looks like a geometric, right, series, right? Because that can be, we have our common ratio here. We just, instead of having the common ratio r, we have the variable r, okay? And so because this is geometric, and this is something we'll need to know in the future, but we know that this will converge when when it's the old geometric, right? If it's just an old geometric with a common ratio r, we know it converges when the absolute value of r is less than 1, correct? So this, and we're going to formalize this a little later, but this will converge when the absolute value of x is less than 1, okay? And you may have to review sort of absolute value and absolute value notation. Remember, the absolute value represents the distance from the origin. If you have this single term here, if your center is at 0, if you're looking, it represents the distance from the origin. And actually, yeah, it represents the distance from the origin. So that means if you take this out of the absolute value, it should be x is between -1 and 1. Okay, and we'll look at that a little later. So this is what we actually would call, for that geometric series, our interval of convergence. okay, which is our IOC, and we will talk about that definitely a little later. Okay, so we can now start example 1. And so I've written it down already, so again, you might have to pause the video and then start it back again. But I want you to observe and just string out the first 4 terms of the following series. So pause the video and just string out the first 4 terms of these infinite series. Okay, so you should have been able to do that. And also on C, it's correct in your notes. I have made an error. It's N should start from 1 because 0, it would be undefined. So this is what you should have. So this is these are all examples of a power series. And what you should notice, and of course I could have simplified, and we will be simplifying them and things of that nature, but they're all polynomials, okay? And so in fact, a power series is an infinite polynomial that's centered at some number C. So let's write that formal definition. Okay, so the definition, we're down here. So power series is an infinite polynomial with center at C. And so this is the general format of our power series. And so that's our center C. Notice it's in the form x minus C. Okay, and that makes a difference. And you have to be careful in case you get something that's a x plus a number, then you have to say x minus the negative of that number. And I know you're like, what is going on? What is she talking about? But we'll look at that in a minute. Example 2, I'm going to try to squeeze in example 2 on this slide because it corresponds to example 1. So example 2 says, go back to example 1 and state what C and A sub n are in the problem. Okay, so let's go back and look. So in part A, and so let's see. So for A, let's look and see if we can state what our C is, which is the center, and what our A sub n will be. Okay, and so if you look, so the center is, let me do this, hold on. The center goes along with the x, right? Because the center is with that x minus C to the n. So for A, what do you think? I'm talking to you, so you can respond back to the video if you want. But in A, the center, what would the center be in A? Very good. Thank you for that response. The center is going to be 0, right? Because there isn't anything there. So C equals 0. A sub n is anything that's remaining from what's not caught up in your x with the x variable, right? And so A sub n, very good, you guessed that correctly, it's going to be 1 over n factorial for number 1, for A, okay? Why don't you pause the video and see if you can figure out what B and C will be. Okay, we're back. And so hopefully you found out, I'm going to look at C first because I'm going to come back to B. But for C, you should get that C is equal to 2 and A sub n is 1 over n, okay? B, this is where I said you have to be careful, right? So the general form, so again, let me go back to the general form is A sub n times that x minus C to the n. So when it's x minus, when it's in the form minus, then you have your C directly. Here in B, it's x plus. So what you can do or just realize is that if you write it in the standard form for our power series, it would be x minus a negative 1 to the n. And so therefore, that's how we got our C equaling negative 1. Okay, so just keep that in mind. If you have an x plus something to the n in your power series, you have to think of that. If you're just looking for the C, it should be x minus the negative of that number. Okay, so now just a little note before we move on to the next example. The first note is a power series is convergent at a value of x if the infinite sum converges to a finite number when evaluated at x, okay? And we'll look at some examples. That's what we're going to be doing to determine when a power series is convergent. The ratio test, for the most part, it's going to be the ratio test, but the root test can also be used if everything is raised to the nth power, but the ratio test is mainly used, so it's often used to determine this convergence or divergence. Okay, so let's look at example 3. So example 3, you have this function, f of x equals 1 plus x minus 2 plus 2 times x minus 2 squared plus 3 times x minus 2 cubed plus so and so on, and If we wanted, we could write the general term of this infinite series. But this is enough to give us to be able, this is a power series, right? And it's centered at what? 2. Good. So this is a power series centered at 2. So I've just chosen these two numbers. So I've just chosen this x here and this x here. In a minute, we'll figure out how to how to determine all the values of x that will make your power series convergent, and thus all the ones that will make it diverge, okay? Because there's a process in determining that. But for now, I just want us to evaluate. So let's pause the video, and we're going to start with the first one. So we're going to start with a f of 9/4. And so just plug in wherever you see an x. This is a function, so wherever you see an x, just plug in. Just from, you don't have to go on past where I went past. You can stop there, but just plug in 9/4. So let's plug it in, and let's see what we get from that. Okay, so if you plugged it in, you should have started off. I'll make that bigger. Okay, you should have started off with something like this, and then once you simplify it, you see you get 1 plus 1/4 plus 2 times 1/4 squared plus 3 times 1/4 cubed. So we now have, because we put in a definite number, we now have a geometric series, right, with r equaling 1/4. And so since we know as long as the absolute value of r is less than 1, we know that the series, right, so the series converges. Okay, so this converges at when x is 9/4. Let's see what happens to 3. So do the same for when x is 3. Okay, so what we notice here, so again, when you plug it in, you should get something like that, and then you can simplify it to that. And this again is geometric, right? But now your r is equal to 1, and so we know that diverges. So it converges at 9/4 when x is 9/4, and it diverges at 3. So the question is, how do we know? How can we find which values it's going to converge? Because x can be any real number, right? Because x is a variable, so it can be any real number. Because for a polynomial, if you remember, a polynomial, the domain is all reals, which means there are no bad values for a polynomial. So x can be any number. So we need to figure out for what values will our function converge, and for what values will our power series converge, and for what values of x will our power series diverge. Okay, so I think I'm going to end this video with just some facts and a theorem, and then we're going to do examples starting from the next video. But these are very important to understand. So let's look at the first fact. Again, I would pause the video and write everything down and then come back, because I'm going to go through this rather quickly. Okay, so f of x, which is our power series, converges absolutely. Okay, so converges absolutely when the absolute value of x minus c is less than r. So remembering the definition of absolute values, this is what that means, right? So that means that we have to take it out the absolute value. We have x minus c is less than r. It's greater than negative r, and then to isolate the x, add c to all the terms, to all the expressions, and so we get that our interval of convergence is this interval here, okay, and we're going to call that, that should say interval of convergence. I'm sorry, I don't know what's going on with my eraser. That should say interval of convergence, or IOC. Okay. And then this R here, that's our radius of convergence, or ROC. Okay. So in other words, f of x converges for x in an interval of convergence, IOC, which belongs to the open interval c minus r, comma c plus r, and possibly one or both of the endpoints. And when we look at the examples, you'll see what I mean. Okay. F of x automatically converges at x equals c. Why is that? Why does it automatically converge at x equals c? So this, if we go back to the original definition, and I know I have a lot of notation here, but notice if, and I'll use a purple marker, maybe a red. So notice if x is c, then what will you get? You'll get c minus c, which is 0, and everything will be 0. So it'll converge to 0. So you will automatically, at the very least, you're going to have one point of convergence. You'll have at least 1 point of convergence. Ideally, C will always converge. Okay, so just keep that in mind. C will always converge. You'll have at least 1 point of convergence, and that's very important to understand. All right. Also note for the interval of convergence. So again, if we're looking at our C minus R, IOC, C minus R to C plus R, and then in the examples, you'll see how to find those. When R is equal to 0, f of x converges only at C. You really can think about this as a number line, right? And so if you're on a number line and that's your C, and the radius tells you how far to go out to the left and to the right, then if R is 0, if the radius is 0, then that tells you that R is 0, right? The radius is 0. That tells you only converge at C. However, again, thinking about this, if your radius is infinity, then in both directions, you're going out into infinity. And so your interval of convergence will be all reals from negative infinity to infinity. Okay, so those are sort of the two extreme cases. We're going to be looking at different cases in between as well. In between for the most part, but those are different. Oh, and I'm also over 15, so let me hurry up and cut this short. And then this final theorem. So again, pause the video and write this theorem down. This is sort of bringing together what we just talked about. So every power series, and that's the general form, has a radius of convergence. So just like you always will have an interval of convergence, even if it's just 1 point for your IOC, you'll always have a radius of convergence. And your radius of convergence R will either be a non-negative number, greater than, so that's R greater than or equal to 0, or infinity. Okay, if R is finite, then f of x converges absolutely when the absolute value of x minus c is less than R, and diverges when the absolute value of x minus c is greater than R. We talked about that already. If R is equal to infinity, then f of x converges absolutely for all x. And when R is equal to 0, f of x only converges at x equals c. So we just talked about it. So I'm going to end this video here and then start the next one with the rest of our examples.